Good evening. I'm here to present a paper titled Be Intentional About Fairness, Size, and Multiplicity in the Rashomon Set. I'm incredibly grateful to having worked with an amazing team comprising of Gordon, Rachel, Emily, and Daniel. So before we get into the specifics, some quick background. Many of you have heard of this concept called model multiplicity, that there are many equivalent performant models for the same prediction task, which could be differing in other behaviors. The related phenomenon have been called by many different names over several years, from Rashomon set back in 2001 to predictive multiplicity in 2020, to leave one out unfairness in 2021, and to under specification. So, but we'll stick to the term model multiplicity for today's discussion. In this paper, we are going to be thinking a lot about the set of equally accurate models for the same prediction task, which we call as Rashomon set. While there has been a lot of work around model multiplicity, we actually don't know much about the Rashomon set itself in terms of properties. In this work, we really try to understand some basics about the Rashomon set and the fairness, and as far as the fairness of models within the Rashomon set. Namely, in this paper, we like to ask questions like, how big is the Rashomon set? How fair is the fairest model? And what an average model looks like? And how do we search for these fair models in this set? And how do individual predictions flip across models in this set? So we explore their policy implications, but I'll not be discussing this in today's presentation. So one main research question, probably the most important that we explore in this work, is what do we gain by being intentional about fairness? So more precisely, what do we gain by intentionally searching over the Rashomon set to find the fairest model, as opposed to choosing an arbitrary model from the Rashomon set? So we find that we can gain a lot of fairness and efficiency through intentionality. So rather than sampling randomly within the Rashomon set, if we search intentionally and search for a model, that will result in much less, that will result in a model that is more fair than a random search. So another core takeaway from our work is that we can calculate the individual flip probabilities. In other words, how likely an individual will experience a change in prediction outcome among models in the Rashomon set. So this will highlight how different individuals in protected and non-protected groups differ in arbitrariness in the prediction that they experience across the Rashomon set. We also derive the Rashomon set as a function of the error tolerance in last sample limit case and the amount of error tolerance used on average. Before we get into the results, let's discuss our formal setup. We think of Rashomon set as a set of models within accuracy epsilon of the base optimal predictor on a given data distribution. So to think about this set of models, we introduce a concept of a flip vector that represents a different model's prediction. So the ith entry of the flip vector is set to 1 if the model predicts differently as compared to that of the base optimal predictor on that point. So then we can show that the Rashomon set is a group of models that have flip vectors such that their dot product with this quantity 2p minus 1, which we call the weight vector, is less than or equal to the error threshold. Then, as we discuss in this paper, we can actually use Gibbs sampling to sample uniformly over the set of flip vectors and calculate their fairness. As I'll show next, we can use this framework to optimize over the set of flip vectors for searching the fairest model. One can think about the optimization problem as a knapsack problem that has a capacity of n times the error, n times epsilon, and setting the theta I value to 1 is equivalent to adding a weight of 2pi minus 1, which is increasing with the distance from the decision boundary, and that has a value which depends on different fairness definitions. So Wi can be thought of as the amount that the disparity is increased, and Vi is the amount that the disparity is increased when an element I is added. So generally, knapsack problem is an NP-hard problem. However, when the number of values are small, as in the statistical disparity case, knapsack can be solved in linear time after we sort the weights in n log n time. When the values are not small, as in the false positive rate and the true positive, false positive and the true positive rate settings, the knapsack can be approximated by a fractional knapsack whose solution is order of 1 over n close to the optimal solution, optimal disparity. So having discussed the formulation and methodologies, let us discuss the empirical results. So one can imagine that within a set of equally accurate models, it might not even be worthwhile to search for fairer models since they might not be that different. So first, our results show that it is worthwhile to search, but by looking at the blue curves on the right, we can see that it's possible to eradicate the disparity even for a small value of epsilon. However, unfortunately, while it can still bring about some benefits, randomly drawing from the Rashomon set is much less efficient to find a fair model than searching a model intentionally. As we can see from the gap created between the blue lines and the green lines in figure 1, searching intentionally for the fairest model within the Rashomon set leads to much fairer models for the same epsilon value than randomly sampling within the set. So we should definitely be intentional about our search. We also derived expressions to understand how likely it is for an individual to get flipped, given that the flip vector is in the Rashomon set. For the large sample limit case, we found that the flip probability is a function of only its weights. Is a function of its weights, and it's independent of each other. One can observe that the flip probabilities depend both on the weights and the epsilon naught from the graphs. Also, the average flip probability across the sensitive groups helps us reason about the arbitrariness of the prediction in the Rashomon set. Here, the bold lines correspond to the protected groups, and the dotted lines correspond to the non-protected groups. And we can see that, for example, random sampling versus optimal search methods leads to model that flip, that basically results in flipping individuals which are more disadvantaged in the optimal case than that of random sampling. Another theoretical result we derived was that of the size of the Rashomon set, which increases exponentially with epsilon. The B of epsilon is the exponential base. And so we can model how fast the Rashomon set will grow from a single model to 2 to the power of n models as a function of epsilon. Since the since the Rashomon set size grows so quickly, companies should set as large of an epsilon size as possible, so that it gives them many more models to search over. One can also prove that a vast number of models in the Rashomon set have accuracy about epsilon less than the base optimal model. And since Rashomon set size increases with epsilon exponentially, many models are on the edge. So hence, while companies should push the epsilon naught as much as possible, they should expect all of error tolerance to be used up. So there's a bit of a trade-off there. So the key takeaways are listed in this slide and have been expanded in the previous slides. And the policy implications have been discussed in the paper in detail. Please feel free to go and check out the paper using the QR code. Thank you so much.
Thank you so much for wonderful presentation. I think we have 3 minutes for questions from the audience.
Thanks so much. Really interesting talk. The very last thing you said raised a question for me, which is it always on the edge? In other words, you have some error tolerance. You're searching for a fair model within models that are some error away from the Bayes optimal model. Is it like, do you have some results suggesting when it will be on the edge or when it won't be? Like presumably if you can achieve zero zero disparity within the Rashomon set, then you can be done and you don't have to give up any more error beyond that. Sure. But thanks for the talk, really interesting.
So the result about the distribution of error is just that most of the mass of the Rashomon set is around the edge. And so when you're sampling randomly, you're most likely to find models within that outer ring that's like very close to epsilon. But obviously if you're searching optimally for fairness, whatever epsilon that you need to minimize your fairness completely, which is often much smaller, that's where you'll stop. So if you don't need your full epsilon allotment for the optimal model, you won't go that far. But if you're sampling randomly from the set, then you're most likely to find one that's from the edge there.
Thanks.
Thank you. Just a question on takeaway 2. First of all, I may have missed it, but how exactly does the flipping differ between being intentional and random sampling? And could you offer any kind of implications for like why that might be?
So can you please repeat the first question?
Actually, I guess that's here, but I guess I'm wondering, like, could you offer any implications or opinions on like why does that flipping differ between or like the outcome differ depending on if you're intentional or randomly selecting?
Great. So if you're uniformly sampling, the space is like pretty huge. It's like 2 to the power of n flip vectors. So you have to be clever in the way you sample and how you sample. But if you intentionally optimize, then we show that experimentally and that it's possible to decrease fairness. So I think if you just do uniform sampling, then the space is pretty huge. So you will not be able to reduce the disparity by uniform sampling. Something clever needs to be done. Which we are working on as a subsequent work.
Other questions?
Which one? Yeah.
All right, let's thank Pavan for his excellent presentation.